Hi, my name is Daniel Gregory, and I'm an assistant professor at the University of Toronto. Thank you for joining me today for this talk that will go over the results of a study I did investigating whether host rocks of particular ages are more likely to host gold mineralization. The premise behind this talk is that sedimentary pyrite or sedimentary rocks more generally are viable sources of gold from mineral deposits. And we know that sedimentary pyrite is enriched in gold at different periods of Earth history. Thus, these areas that are more enriched in gold, or the rocks underlying them, are more likely to host gold mineralization, as these are better source rocks. Over the course of the talk, we'll go over the model for sedimentary hosted gold deposits, and then we'll go through the periods of geological time where we've outlined that sedimentary pyrite is particularly enriched in gold. And then we'll go to an example from Queensland, Australia to see whether gold prospects are actually more commonly associated with rocks at these ages. So what much of the premise of this talk and study is based on is what the best source rocks for gold deposits are. And if we look at this chart in the orange, we can see that the highest gold of average rocks is carbonaceous shale, which would suggest that it's a pretty good gold deposits. However, tholeiitic basalts are also good sources of gold. However, if we think about the other elements that are enriched in gold deposits, often one of those elements is arsenic. And while tholeiitic basalts might have quite a bit of gold, they don't have much arsenic. However, our carbonaceous shales do have quite a bit of arsenic. So if we're looking for an arsenic-rich gold deposit, our better source rock is carbonaceous shale, though tholeiitic basalts can be viable sources in some circumstances. So how this works is gold is brought into the sediments in two different ways. One would be detritively adsorbed onto clays, or just in detritus more generally, or we can have it precipitating out of seawater in euxinic settings as sedimentary rhamboidal pyrite, or adsorbed onto organic matter and settling into the sediments. Then during early diagenesis, though that gold and other trace elements goes from the organic matter or clays and is incorporated into pyrite as diagenetic pyrite forms. So it goes from the organic matter and into the pyrite. And then during late diagenesis, the pyrite is recrystallized or converted to pyrrhotite. That releases the gold and other trace elements into metamorphic fluids, where they travel to favorable structural sites to form the gold deposit. Now, I want to do a quick note here that sediments aren't the only source of gold. However, we shouldn't get too preoccupied with just the most important source of gold, because if we have an upgrade in many of these systems, just adding 10%, say, from the sediments would be enough to bring something up to an economic value. So if we have an intrusion-related magmatic gold source for most of our gold, we're still better off if it's intruding into gold-rich sediments, because that could remobilize some of that and bring our deposit from being an anomaly to an actual deposit. So how does this help us find gold deposit? Well, it does a couple of things. It can let us find different periods in Earth history when sedimentary rocks are particularly enriched in gold, and these can be good targets for greenfields exploration. Or it can also allow for initial testing whether basins are good source rocks. So under this idea, we could go to a basin that hasn't seen a lot of exploration activity, analyze the pyrite in the sedimentary rocks, and if they are high in gold, that would suggest that we should look at this basin a little bit closer. So what we did when we were about 5 years ago when we were building this up is we took shale samples from all around the world and trying to get as much coverage for different periods of geological time as possible, with the idea that we would see if there are different periods in Earth history, due to different climatic or tectonic features that are particularly enriched in gold. And this is the result of the average of our analyses. And in many times we would try and get multiple samples from different basins of the same age so we can see if it's a global rather than local phenomenon. And we can see clearly that there are a number of high points, especially in the Proterozoic and Archean, and I'll talk about the Phanerozoic separately later. And here we can see the different high points we identified, and these tend to match with different periods where we have the ages of the host rock of important gold districts, like the West African deposits here. The Yilgarn Superior craton deposits are hosted by rocks of these ages, and then this is the age of the Witwatersrand deposit host rocks. And we see a similar thing, although it's more variable, which might be a function just of sample density, because there's a lot more Phanerozoic rocks. And these two match the ages of host rocks for major gold districts, like the Carlin deposits here. And here at this time period, the Lachlan, Kazakhstani, and Sukoi Log deposits. And in all, we identified several different time periods of gold enrichment in sedimentary pyrite, and they tend to match the ages of known gold districts. So what we thought we should do was try and go into an area that isn't particularly known for a lot of important gold mineralization, but it should be noted that gold occurs many different places, and there are some deposits in Queensland. So we wanted to test our area in an area that doesn't have these major gold districts, just to make sure that we aren't overwhelming our system by going to Carlin, and we already know that the host rocks are the right age, and lo and behold, the Carlin are all found in that age of host rocks. And we also wanted an area that was relatively sparse in the age of prospective stratigraphy, but still had some. And Queensland was a good match for this, and it also had a decently well understood geology, high quality geological maps that were readily available in an easy to use format. And this map shows in black the time periods of prospective stratigraphy in Queensland. And if we overlay the known gold deposits and gold anomalies, we find that of the 8,658 total known gold deposits and anomalies, 35% are hosted in the prospective stratigraphy, and that prospective stratigraphy is just 5% of the state. So that's a pretty important finding. And in addition to that 35%, 10% are within 1 kilometer of that prospective stratigraphy, and an additional 18% are within 5 kilometers of that prospective stratigraphy. So just to look at this map here, the yellow is where it's in the prospective stratigraphy. The orange is where it's 1 kilometer away from the prospective stratigraphy. The red is 1 to 5 kilometers, and the purple is greater than 5 kilometers from prospective stratigraphy. That being said, this is only showing surface geology, and some of that prospective stratigraphy could be at depth and still a viable source of gold. If we look a little bit closer in some of these areas that are shown in these boxes, we can see that not only do we have this large number of yellow spots, which are indicating the deposits in the prospective stratigraphy, there's also a number of clusters sort of adjacent to these areas of prospective stratigraphy, and these could be indicating places where this prospective stratigraphy is actually at depth and still a viable source for these deposits. Another area to note is over here in this green one, where we have a number of points that are kind of clustered around, but maybe not in the prospective stratigraphy. And with that, I'd like to thank the sponsors of my research, both past and present.